welcome you all to this. In the last class, what did we cover? That is, given the Wyckoff table, okay, how to use it to generate crystals, okay, having different stoichiometry, okay, all these things which we considered, correct? So essentially, in that one, the last slide which we used was to generate a crystal with P4 symmetry, okay, and having stoichiometry AB2, okay, and with two different molecular formula. One is having a AB2 stoichiometry, this one molecular formula, another is A2B4, correct? In this particular case, if we consider, this is a one type of an atom between two types of another atom. So essentially, this will be at a position which is exactly the middle of it, because the force of attraction or repulsion, whatever you look at it, it's going to be equal on either side. You look at these cases. Here what happens? Here these are like atoms which will have a repulsive force between them. These are unlike atoms which can attract each other. Because of this, depending upon the energetics and the type of interaction, whether it's a covalent or ionic type of bonding, these atom positions could move in these directions, correct? But even if it moves from here position to a closer position, if you look at the symmetry, remains the same, that doesn't change, right? The exact position atoms occupy in the crystal can change depending upon the type of atom which is involved, the types of atom which are involved, but the symmetry remains the same, that doesn't change, okay? So far what we have considered is, if you have to construct a perfect crystal, okay, what all information which we require. Okay, perfect crystal means that a crystal which doesn't contain any defects, okay. Then one, we should know what is the crystal system in which we want the crystal to be, correct? So this we are considering it that we are trying to construct a crystal. Then another is the other primitive or whether it is a non-primitive lattice, okay. That information is necessary, okay. Then what are the lattice parameters which the crystal has, okay. Then what are the elements which constitute the crystal structure, and whether the elements occupy positions randomly in the lattice or they occupy some specific positions. That is that information. That's whether it is ordered or disordered. And then what is the molecular formula which compound should have in that unit cell. That also decides which position the atoms will occupy in the crystal, okay. If all this information is available, then we can construct a crystal looking at, okay, the Wyckoff position table which is given. The other one which is available in the International Union of Crystallography is the symmetry diagram, two-dimensional representation of symmetry, and also the position of a motif or an atom if you put at a general point, how it is distributed, okay. But this Wyckoff table is the one which is most important as far as construction of crystal structure is concerned. We will go into it in a little bit detail, okay. The first thing is that all these crystals, if you consider three-dimensional crystals, these are all based on 14 Bravais lattices, correct? Essentially putting atoms at different positions in the lattice, okay, whether it's a general or special positions, we generate different types of crystals with different type of space groups, correct? But how many types of lattices which we can have? They are only 14, okay. So the one is, the lattice could be a primitive lattice, correct? If a lattice is a primitive lattice, then we have to then one has to mention only that one position, which is the lattice point at the origin if it is mentioned. All other lattice points could be generated, because suppose we, therefore it is a primitive lattice, all primitive lattices, only one lattice point will be given. Okay. Once that lattice point is given, then by applying the translation symmetry, we can generate all of them. This will become 1 0 0, then 0 1 0, okay, 0 0 1, 1 1 0, okay, 1 0 1, 1 1 1. Like that we can go ahead and complete that full unit cell could be constructed, because this way, using translational symmetry and knowing the position of the atom at the origin, the lattice point, we can construct the lattice, correct? If it is body centered lattice, it does not matter whether it is a cubic or whether it is tetragonal or whether it is orthorhombic. Okay. Two lattice points are there in that unit cell. One lattice point is at the origin, another lattice point is going to be at the middle. So, this will have coordinates 0 0 0, this will have coordinates half half half. Okay. This is distinctly different from the primitive lattice, in the sense that from this lattice point to this lattice point, by a lattice translation vector, okay, and the symmetry of that point is that site symmetry M3 bar M, okay, and it is designated in Wyckoff terminology as A, okay, and how many points are there? The lattice, that is only one, okay. Then as I mentioned earlier, okay, if you are trying to construct a lattice, or if you are trying to construct, not lattice, a crystal, okay, using only one element, any one of these atom positions could only be filled, correct. If we are keeping an atom in the simple cubic lattice, okay, at a general point, then another 48 points related by symmetry, we have to keep the atoms to generate the simple cubic lattice. You understand? That is what this is being shown. And there are others with, when it is being kept on some other symmetry elements, these are all the positions which are being given. Is it clear? So, in a simple cubic lattice, if you do not keep atom at the lattice point, put it as a general point, like somewhere here, if you try to keep an atom in this lattice, in the simple cubic, then the number of positions in which the atom has to be there is 48, or a simple cubic lattice, when we place an atom, okay, at a random point within the unit cell, there are another 48 positions are there which are related by symmetry, at which the atoms are there. Okay. Normally the lattices which we consider for when we try to fill up the different special positions, the one which has the highest symmetry is what is filled, okay. That turns out to be this particular position, okay. So, we get a simple cubic crystal structure, okay, with atom occupying the lattice point, correct. Then the unit cell will have 48 atoms in it. That is a maximum which it can have. On this basis, if you consider how many atoms are required to construct a FCC lattice, putting an atom at a random point, that is 192 atoms will be there if we place an atom at a random point in an FCC unit cell, the crystal to exhibit that FCC. Because 4 the FCC lattice contains 4 atoms per unit cell. Similarly, body centered, if we consider, okay, cubic lattice, it will have 96. Okay. That is, and another important factor which you see, that here I am showing it for the body centered unit cell, all the Wyckoff position tables which are available. If you see here, one thing which will be mentioned as the coordinate 0, 0, 0 plus half half plus. This means that these are all the 2 lattice points in the Bravais lattice. Okay. And here the coordinates which are given is 1 with respect to only the origin. And if you see, this is the symmetry of the point, okay, and then 0, 0, 0, its Wyckoff position is A, and it's mentioned always that 2 atoms have to be there. Okay. How do you generate the atom in the second position? That is, to these 2 lattice points you add this particular position where that atom should be there. If you add it, this will become 0, 0, 0 and half half half, correct? So, these are all the 2 positions the atoms will be there in the, if it is a single atom, if you consider it. Okay. Suppose you are placing the atom not at the corner, but at the face center. Okay. Then these are all the 3 general positions which are in fractional indices, and with respect to origin, where one of the lattice point you take these 3 positions, you will be able to generate. Then with respect to the other non-equivalent point in the crystal, you will be able to generate another 3 more. So, total 6 positions where the atom will be there. Is it clear? That is, the atom is being put at this particular special point if we try to keep it. Or it so happens that we assume that this crystal body centered unit lattice, but it contains 6 atoms. Then what is the position which it can have? Then the atom has to occupy only this particular one. Is it clear? What we will do it is that some of these things as an assignment we will work it out on this Saturday. Okay. Then it will become very clear to you. Similarly, in FCC, if we consider what all the lattice points are there, lattice points are 4 points are there, correct, within that lattice. And with respect to these lattice points, around each lattice point, these are all the positions which we can have the atom. Then if we add with respect to each of these coordinates which are given, we will generate 4 points, okay. And that when they are occupied, a simple cubic lattice like copper, aluminium, gold, nickel, all these elements we can generate, because there are only 4 atoms per unit cell, correct? Is it not? That is the way this is going to be filled up, okay. Here what I have shown is comparing between 2 primitive lattices of the cubic unit. Okay. This is PM3 bar m. Okay. I had just shown the few, not the complete coordinates for all the Wyckoff positions I have not shown. Here it is for P432. Okay. This is also a primitive lattice, okay, cubic. Okay. But the space group symmetry, these 2 are different. Okay. What is this M3 bar M means? Actual symmetry elements. Four by M, 3 bar, 2 by M. This is the full symmetry element which is associated. You should remember all these also, because what is given is a convention, is a shorthand notation. Okay. Is this clear? Okay. Here if you look at it, this is also a simple cubic lattice, okay, this is symmetry. This is also 432. if I take an atom, atom has got an infinite symmetry, right, assuming to be a sphere. Then if I place it at the simple cube at 0 0 position, okay, then what is the symmetry which it will exhibit? What is the symmetry the crystal will have? 432 or PM3 bar M?
Sir, both of the symmetry element will be there.
Both of the symmetry elements. But which has got the maximum symmetry element?
M3 bar.
M3 bar M. So that symmetry element it will exhibit. So if you see here, all these Wyckoff positions up to a certain point here, these Wyckoff positions remain that same, identical. So which, because it's a simple cubic unit cell on which if you try to fill up, okay, these positions, they are all identical positions. So then the symmetry which it will exhibit is the one which is maximum which it can have. But only here when you come to this Wyckoff position and here this Wyckoff position, you find that suddenly there are differences in the atom position, okay. Only when we place atoms corresponding to these positions, then only the difference between these two structures will come. Is it clear? What does this suggest? That only when we have a large number of atoms are there to be placed within the unit cell, then only the subtle difference between these two primitive lattices with two different types of symmetries which we see the difference. Otherwise, if it's only one type of an atom and we are placing it at the lattice point, it is like it will exhibit the symmetry of the lattice. What is the symmetry of the lattice? For a simple cubic lattice, it is PM3 bar M. So that's the maximum symmetry. Okay. The subtle differences in symmetry come only atom is kept at positions where, okay, the number of atoms which has to be kept at, for some Wyckoff positions we see the difference. Only when those Wyckoff positions, that is the number of atoms per unit cell, suppose for a simple cubic lattice turns out to be 24, okay, then the options are whether it can be filled in this way or it can be filled in this way. If the atom positions are kept at these particular positions, then it will turn out to be PM3 bar M. If the atoms are kept at these positions, it will give a symmetry which is P432. Is that clear? Okay. So far, whatever the symmetry diagram, okay, and the positions of general point, okay, in the unit cell which has been shown in the international crystallography, whatever I have considered are with respect to structures which have less number of smaller symmetry. Okay. When the symmetry becomes large, this is PM3 bar M I have taken, you can see the type of symmetry elements which are involved are much more complicated. Okay. When we look for a FCC structure, it becomes still more complicated. When we look for a diamond cubic, okay, where a glide also is there, screw comes into the picture, then this becomes very complicated structures. Okay, that's, so you don't have to really bother about it. To construct a crystal structure, what we require is the Wyckoff positions and the coordinates which is given in the International New York crystallography. That itself is good enough to construct a crystal structure. Okay. Here you can see that how the atoms are distributed around the lattice point when it is being placed at a general position. Okay. So as I mentioned, that composition is necessary, okay, if more than one element is there. If it is disordered, then atoms can be randomly placed at any position, lattice point. If it is ordered, then we should know which particular type of Wyckoff position this atom is going to occupy. That also will be decided by the molecular formula of the crystal structure. So all this information we can get it from International Union of Crystallography. If you look at many of the crystal data presentation, okay, in many of the books which are given, okay, there are many symbols. Pearson's handbook also, if you look at it, okay, they follow a particular system. That is quite often for most of the elements where the crystal structure has been identified, elements or many compounds where the crystal structure has been identified, it is tabulated in some form. It's available in some crystal data set. Okay. In that they follow a particular symbol to explain this. One, triclinic is essentially symbol which is used DCA, okay, and if it primitive is with respect to P, okay. If it is monoclinic, it is M and MP, and that MS is used where it could be MABC. Okay. Similarly, orthorhombic if we use OP, if is O is for orthorhombic, P is for primitive, OI is for orthorhombic for body centered, OF is orthorhombic face centered. Okay. Like that we have these symbols. Okay. This Bravais lattice symbol just tell, okay, what is the crystal system to which it belongs and whether it is primitive or a non-primitive lattice, right. To give the complete information, one more information which is required is how many atoms are there in that unit cell, right. Like triclinic, if you say AP, the last number N, this number could be this number can have different values. Like for example, suppose it is copper, how will we represent? What is the symbol in this notation? C? Yeah, CF4. This is what it will turn out to be. Suppose it is diamond.
CF.
It will be CF8. There are going to be 8 positions. Motive or an atom or a molecule is going to be kept. This is how this representation is. Okay. Is this clear? This is the way it is represented in many books. Okay. That is what essentially given in this table also. Okay. Then when you go through papers, you will find that to describe this crystal structure, there are many types of symbols which are being used, right. In most of the metallurgical journals, if you see that A1, A2, A3, A4, A5, then B1, B2, then C1, C2, C3, DO3, DO22, L12, L10, this sort of symbols you will notice, correct. That is one, that is called structure barrack. This was one of the oldest one. Then the Schoenfly symbol is the one which what the chemists use it, which just represents what is the type of symmetry elements which are rotational and inversion, okay, mirror, all these things are associated with it. Then the other way is that we can use that just the unit cell FCC, BCC, this also we see this type of nomenclature used. Then Hermann Megwin is the space group symbol which we will be noticing it, and nowadays this is the one which is used as a standard symbol. Okay. This as well as this symbol is the Schoenfly symbol, these are all the two, because mostly the solid state chemistry people who work on crystallography, they use this symbol. Material scientists use these symbols. Okay. And then typical what is the element which is a element or a compound which is having that crystal structure, that also that information is always given. Okay. Okay. What are the ways in which we can represent these structures? Okay. One is construction of a unit cell, which we have looked at it, how to construct a unit cell. Another is arrangement of two-dimensional layers, one on top of each other, right. Like for FCC, if you take A, B, C stacking sequence, okay, A layer, B layer, C layer, that is on top of a hexagonal lattice, okay, one on kept on top of the other at some different positions. we can generate this lattice. That is what essentially is being shown, and in the unit cell form also we can represent them. Other way it will be represented is that not only just you do not have to show all the atom positions, you just show the points, non-equal points where the atoms are going to be by that is 0 0 0, the coordinates are given here, right. Then this one exhibits, okay, this figure tells us about what is the primitive lattice of FCC. Okay. Here it is essentially a rhombohedral lattice or trigonal. Okay. This is one coordinate. So, it is essentially all these three together, okay. Half of 0, half 0 half and 0 half half. They are the ones which once the three lattice parameters corresponding to this trigonal lattice. Okay. This way we can construct it, and this has only one atom per unit cell. So, it is a primitive unit cell. Okay. And this is the way we will be representing this coordinates of this lattice in terms of the FCC coordinate, correct. Similarly, we can have hexagonal lattice also. We can represent it in this form. It is an AAA, and HCP, as I mentioned, is not a Bravais lattice. Okay. So, it will have two positions, the A, B, A, B. So, essentially if you consider two lattice points together, that determine the Bravais lattice of hexagonal closed pack. Okay. And this is the another way in which we can represent the projection also, right. And then at what position these atoms come, that also we can mark it to explain. The same way we can represent body centered cubic lattice also. Okay. The various representations are possible, and here this one is essentially the rhombohedral lattice, okay, unit cell, and this is nothing but a primitive lattice. Okay. But what is the difference between this primitive lattice and the FCC lattice, FCC or the BCC lattice, is that the BCC lattice exhibits the complete symmetry of the lattice, whereas the primitive lattice which we choose, that does not exhibit the complete symmetry. Okay. And these are all the various ways we can project it also, the lattices. Okay. This is for an FCC lattice.
We should represent primitive lattice. So
Why don't we represent BCC as the primitive lattice?
We can represent it as a primitive lattice, but the problem which happens is that when you represent it as a primitive lattice, okay, the symmetry, complete symmetry, you do not see it in that unit cell.
in BCC you can see.
No, BCC you have the full symmetry is there. The symmetry of the BCC lattice can be seen in the BCC unit cell, but not in the primitive, because BCC unit cell is non-primitive. Okay, rhombohedral is the non-primitive unit cell. Okay, that does not exhibit that symmetry. Okay. So, what is the other way in which this could be represented? The projection, we can take it along any particular direction and then show these are the atoms which are there in the projected layer, okay, which is 0 0 1, and then atoms at other positions, they can be represented with different symbol and we give the coordinates. Okay. Or we can just give with these positions, which essentially tells that it is half a layer up. Okay. That is another way in which we can represent them also. We just use two symbols, but you just write it down, 0th layer and half layer. This sort of notation, when you go through many of the published papers, you will find all types of notations are used to represent unit cells. This is called as a Wagner-Seitz cell. What do you understand from this? Primitive. What else? Yeah. this lattice exhibits, this is a primitive lattice which is constructed, which exhibits the full symmetry of the crystal structure. Okay. How is it constructed? From the origin, okay, find out all the nearest neighbor points, okay, draw lines to them, find out the midpoint, draw a plane normal to it. Okay. When you draw a plane normal to it, all these planes will intersect and it will enclose a volume, correct? This volume, within that only one atom is there, and this has a specific shape which is associated with it. And if you look at the faces which it has, it exhibits the full point group symmetry of the crystal it exhibits. Okay. Here what we have is that a hexagon and a square is the one with which the surfaces are formed for BCC. Okay. This is called as a Wigner site cell. Okay. A similar correspondence to this in another cell is there in reciprocal lattice. You know what it is? Wigner cell in reciprocal lattice. It can be any structure, because Wigner cell is for all the structures you have. It need not be for FCC or BC. It's for every non-primitive cell we can construct one. You heard of Brillouin zone, na? Brillouin zone is nothing but in reciprocal space Wigner site cell. Okay. Corresponding to Brillouin zone in real space, what you draw is Wigner site cell. Okay. What is the importance of this? Is that whenever some computation you wanted to do, okay, you have only, it's a non-primitive lattice at one lattice point. If you take the electronic structure, whatever is the property corresponding to this cell, and it can be by periodic, it can be repeated in the full space, and you can do it. For computation becomes much easier. So most of the time you will find that this sort of cells are used. Another name also which is used, that Voronoi polyhedra. That's also another name which you will see it in. This name you will see in many books using this name also. This is all nothing but the Wigner site cell. Okay. This is a primitive cell which exhibits the full symmetry of the lattice. Okay. And the construction is explained how to construct this cell. Okay. Is it clear? If you have any doubt, please do clarify. Okay. Similarly, for FCC, if you try to consider, this will be essentially like rhombuses. Okay. That is essentially 110 type of surface with which that polyhedra will be made up of. Okay. So once we have got a specific crystal structure with a lattice parameter which we know, okay, this is considered for a cubic structure. Okay. We can do it for a tetragonal structure also. There we should know the lattice parameters, right? Then you will find that depending upon the lattice parameter ratios, okay, there will be some small changes which once you draw, it will become very clear to you. Okay. This sort of cell can be constructed. This is a very important aspect, okay, of geometric crystallography which one should always remember. Okay. Now, you have studied that in crystals, like if you take a simple FCC lattice, if atoms occupy all the corners at the face centers, okay, there are tetrahedral and octahedral positions, correct? These are all the positions where normally we say that the interstitial atoms can come and occupy position. It need not be interstitial. The second element can come. If that first element has occupied this position, the second element can come and occupy this particular position. Okay. What all these positions correspond to? These are all special points in the crystal which if you see here, okay, here I had just taken a few Wyckoff positions starting from the one having the lowest highest symmetry and going up with lowest symmetry I had given. Okay, if you look at it, these are all the positions. 0 0 0 represents the position which corresponds to a lattice point, and when we add to the other 4 equivalent lattice points, we can generate all the points. Okay, then we have to apply the translation symmetry rule. Then we will be able to find out what all points in the unit cell atom should be kept, and then we can complete the structure. Okay. Which is the next position which it can be filled is M3 bar M, the same site symmetry as the origin is there at the center. That position, 4 positions are possible, equivalent positions are possible. Okay, this is half half half. If we add this to these equivalent positions in the lattice, then we will be able to generate all the positions and generate these are all the positions where atoms can be kept. Okay. This could be interstitial or this could be another. This is how most of the lattices, okay, ordered lattices are generated. Okay. And then this position if you try to fill up, okay, this Wyckoff position C, then this will all correspond to tetrahedral sites. This we call it as generally as octahedral sites. All these sites are, as per the Wyckoff table, special positions in the unit cell. You understand that? So if we try to fill these positions, okay, then what is the type of a structure which we will generate? What will be the stoichiometry? That is, A atom is placed here and B atom is placed here. AB type of a stoichiometry. Which is the crystal which has this stoichiometry which it forms? NaCl, okay, titanium nitride. There are many compounds are there which form with these crystal structures. Okay. This is how it happens. Suppose in a titanium nitride or sodium chloride, these positions are occupied. Now which is the next position, interstitial position which will be there? Then only the tetrahedral positions are available, to which the third atom if we wanted to put, they can go and occupy. This is how the crystal structures are constructed. Okay. And then the compound will have A, B, and if it is achieved, A, B, C2 will be the stoichiometry of this particular compound. Right? Is this clear? Okay, I will just leave this. Okay. This I had already explained in the last class, how in that Pearson's data book they give all this information, correct? In the last class I mentioned like cubic structure, okay, the lattice, yes?
In the FCC lattice, even the body center has M3 bar insulated.
Yes, the symmetry, the side symmetry of this position and this position remains identical. Yeah.
Why is it not that any atom is occupying that position in the first place? Why is it as an interstitial?
If you put an atom at these corners and if you put at that position, it becomes a BCC.
Like all the corners face it and the body center.
No, the first rule is that only one special position can be filled with a one particular type of an atom. If you put the same type of atom on 2 Wyckoff positions, then the symmetry of the lattice changes. Symmetry will not be the same. How do you identify a symmetry? Is the environment remains identical, correct? That's if you put a position at that position, that environment, the same position if you atom you put it, the environment changes. If you put a different type of an atom, then the environment around it doesn't change. That is the main governing rule in constructing these lattices using this Wyckoff table. Okay. Like diamond, if we take it, the lattice parameters and Z equals 8 means that the molecular formula, that is the total 8 atoms are going to be there in this. Space group is F D 3 bar M. Okay. This is the number also which is given. This is the space group number which is given in the International Union of Crystallography. So, we can go to that page and get all other detailed information, and atomic positions are only A positions are occupied, but 8 atoms will be occupying this position within the unit cell. Okay. Once this information is there, we can construct the crystal structure. Essentially, this information has been obtained from X-ray diffraction or electron diffraction, various information, when the complete data analysis has been done. Okay. And the complete crystal structure information is given. It is published in these books. Okay. Similarly, we can consider it for BCC. Okay. Here if you see it, the atoms occupy the lattice points which correspond to this A position, Wyckoff position. Okay. The other Wyckoff position the next atom can occupy is that 4 by MMM. Okay. If you look at this Wyckoff position, what is the symmetry of that position, that site? That is a tetragonal symmetry, right? That is M3 bar M. That is, if it has to have a cubic symmetry, that is, the atom can, the crystal can have as a whole a cubic symmetry, but each lattice position can have a symmetry which need not be cubic. How is it determined? Is that if you look at this special position, what are the positions at which the nearest neighbors are there, whether they exhibit the cubic symmetry or not, this case you look at it, that tells you what. If you look here from this position, this 1, 2, 3, 4, these are at a by root 2 distance. From here to here and this is at a by 2, correct? So, 2 are, and they are 90° perpendicular to each other, these two. The third, which is perpendicular axis, is at a distance which is not the same. So, the symmetry which it exhibits is a tetragonal symmetry. That is what essentially, that is what is being represented here, this site symmetry. Okay. So, this is what we, this is an octahedral cage, correct, where an atom can come. The other is that if you see the next one, it is the, with respect to a lattice, it is tetrahedral position. But if you look what is the symmetry which it has in cubic, in body centered, it is 3 bar M. Okay. It is a rhombohedral symmetry. Okay. But if you look here, this particular position, it is essentially 4 bar M2. This also exhibits a tetragonal symmetry, this side. So, either this gets filled, or the next site which you always find is that these are all the positions which the atom, because that is having a lower symmetry compared to the other one. Is it clear? So, this is how finally the symmetry determines. First we take an atom and we know that these are all the positions which are available in the unit cell where we can place it. Then it will occupy those points which has got the highest symmetry. Once that is completed, the next atom will go to a position of the available special positions which are available, which has got the lowest symmetry. It will go to that position. That is how the lattice is generated. That is how the crystals are generated, by placing atoms at different positions. Okay. This is, I had just shown it for HCP lattice, which one can fill it up similar way. Okay. This you can work it out. So, here again structure based on filling up of interstices, FCC lattice, which we are familiar with. Okay. This is a sodium chloride structure. Okay. A titanium nitride also have the same structure. The anions occupy the corners, the cations occupy the face centers and the edges. Okay. edge center. This is how the structure is generated, correct? And in this, with respect to the Bravais lattice, each lattice point has got 2 atoms per lattice point, correct? Is it clear? Because around each lattice point, one position and one more position which will be there, that's 2 atoms are going to be there, because how many atoms are totally there in this cell? 8. Okay, one Na and one Cl occupies each of the lattice points. That's the way it is. Okay. Similarly, suppose we try to fill the tetrahedral lattices, then what is the stoichiometry which this material will have? The tetrahedral positions are C, right? And this is A, 4 and 8. So it has to be essentially AB2 type of a stoichiometry which it should have. Okay. A typical example is calcium fluoride. Okay. If you see, that has ABC, the calcium atoms occupy all the corners, the fluorine atoms occupy the centers of the tetrahedron sites. Okay. And this also can be represented as like around each cation there are anions which are situated. This cage is essentially a tetrahedral cage, right? Because so far here we have considered only how many atoms are there, total number of atoms which are going to be there. 12 is going to be there, correct? And like earlier class, we considered that we can have like for M23C6, 116 atoms could be there. So if you have to place all the 116 atoms in the unit cell, it's going to be a very big mess to visualize it, right? In the unit cell, one way in which we can represent it is this sort of cages if we consider around cation or an anion, and we can construct the crystal structure that way as well. Okay, we will come to it. Similarly, another structure is called as an antifluoride structure, where the lithium atoms, okay, these are oxygen and lithium. The lithium ions are kept at the, so oxygen atoms come at these positions. Okay, this way also we can. Okay. Here also we have 3 atoms per each lattice point we will have. That is with respect to a Bravais lattice. Then here is this diamond is also a lattice which is based on, it's a crystal which is based on FCC lattice, correct? The number of atoms per lattice point will be 2 in this particular case. Earlier we have discussed what are the various ways in which it can be represented. Okay. Here what is going to happen is that if we divide this lattice into 8 smaller cubes, okay, at the center of these 2 cubes if we place another carbon atom, with respect to a bottom the center of this one and the one with respect to the center of the bottom half if we keep, then we will be generating the diamond structure, right? Essentially with respect to, if you look at the bonding with respect to every carbon atom, okay, it's a tetrahedral bond, 4 carbon atoms are there, okay, bonded to it. Okay. Another type of a lattice which we can consider it is, because I am just taking FCC as an example, FCC lattice as an example. Okay. Similarly, we can take with respect to all the Bravais lattices, okay, we can fill it up this way and construct various types of crystals can be constructed. Okay. This we will give it as some assignment to you people to work it out. Okay. Here on a zinc blende, that is cubic zinc sulfide. Okay. There are two forms are there, hexagonal as well as the cubic. Right. This is zinc blende, another is the woodsite. Here if we consider it similar to diamond structure only, okay, all the corners or face centers are occupied by zinc, and the sulfur occupies 4 positions inside at 4 tetrahedral positions out of the 8 which are possible, right. So here also this sort of representation which we can use to fill up the lattice. Okay. Here I have just considered perovskite structure, barium titanate is one example, okay, and these are all the atom positions which are there. Okay. This is a primitive lattice. Okay. Yes.
Sometimes it can occupy half the total number of positions as well, right? Like in ZNS, sulfur occupies half the 8 positions, half of the 8 positions.
Suppose the sulfur occupies the other half also, the stoichiometry will become Zn S2. Okay. But electrostatic charge balance has to be maintained, that decides what is going to be the stoichiometry which the material can have. That depends upon the balance of the elements which are involved.
The total number of positions can be filled, or is it like what?
Like carbon, if you say the diamond. Diamond is also out of the tetrahedral positions 8 which are possible, only half the positions are occupied. Yeah, it is possible.
Positions are similar positions, right? Earlier when we saw,
No.
we are putting an atom at one point, we have to, to maintain the symmetry, we put it in all the similar points, right?
Exactly.
So how do we explain this in this case?
Yeah. What you have to consider it is what are the lattice points where we can have the atoms, correct? If you look at the Wyckoff table which is given here, okay, with respect to diamond cubic, it is a face centered but D3 bar m, okay. So since it is a face centered lattice, these are all the 4 equivalent positions are there. Around each lattice point, these are all the positions where the atoms are going to be there. It is not the same as in FCC. The lattice is FCC, okay, but around each lattice point the atom is occupying some special positions. You understand that? When we filled up in this particular structure, here it is essentially the Wyckoff position table which we give it is for a structure which is essentially an FCC structure. You understand that? Here the symmetry is not the same, so essentially these two are slightly different, but the lattice essentially is an FCC lattice. You understand that? That is a subtle difference between them. It is not filling up of some of the positions in that FCC lattice. Is it clear? These are decided by the type of bonding which we have. Okay. So here if you consider barium titanate, okay, the number of atoms in the unit cell, if you see, this is what essentially it is going to be the total number of atoms around each unit cell to have this molecular formula. Okay. Then you can make out that showing the positions is going to be quite tricky, right, and it is very difficult to visualize it. The one way in which it is being done is that if you show with respect to a cage, this is an octahedral cage in which the red atom, yeah, is kept here, and these are all the oxygen atoms. Now it becomes much easier to understand this, right? That is, these are all the positions one type of an atom occupy. These are all, and then this is the another position, That is, this is one which has an AB O3, right? A atom occupies one particular position, all the B atom occupies another position in the primitive lattice, okay, and the C atoms are the oxygen atoms which occupy these positions. So, this way also we can represent it. You will find in many books this sort of a representation is being given to describe these structures. Okay. You know what is the property of barium titanate? It's a piezoelectric. So, piezoelectric means that what it should have? It should be a polar molecule, right? By application of stress you should be able to. Okay. But looking at it, do we see any of these? From the structure it looks like a cubic structure, right? When it undergoes the transformation, there is a slight distortion is there, okay. I will just come back to this. That is, these cages are essentially to maintain the charge balance, there is a slight distortion. That distortion is, one you see that it is tilted in this, another is tilted in a slightly different way, because this is the same type of octahedron when it comes. With respect to a charge, if we consider it, all the positive charges and the another negative charge which comes at the center, they are going to be slightly displaced. So, it is essentially only a tetragonal structure can exhibit that. Cubic structure, by symmetry they have to coincide. So, it cannot exhibit, all polar molecules cannot have a cubic symmetry. Understand that?
So they are distorted only along this axis.
Along this axis.
Other axis.
Like that, in another unit cell it can be along all the three are equally possible. That is why we say that this can exist in three variants. Okay. These three variants are called as orientation variants. The three orientations it can choose. Okay. And this is another form in which it is exhibited, where this is where the atoms are slightly shifted the central atom, because of which it will exhibit this piezoelectricity or ferroelectricity. All these will have this sort of crystal structures. Okay. That is just looking at from the crystallography itself. If we find that this is the property which it exhibits, we can expect what is the positions which atoms should occupy. Okay. That some guidelines we can get it. Okay. Similarly, we can take a cesium chloride structure. Okay. This is a also a simple cubic lattice, right? Two interpenetrating. If the atom turns out to be the same type of an atom, it will be a body centered. Okay. That is, a disordered lattice will be body centered. The ordered lattice is essentially a primitive lattice, primitive simple, that is a simple cubic lattice. Okay. Here also, in these sort of lattices we can fill atom positions, okay, and various types of crystal structures could be constructed. Okay. This is essentially with a tetrahedral, that is, here also wurtzite, zinc blende, carborundum, there are many forms, okay, which are possible, with various types of stacking sequences are possible. Okay. Like hexagonal lattice, what we considered is essentially AA is one type of a hexagonal lattice, right? Another is this is hexagonal, this is hexagonal closed packed. Okay. Another type which we can have is this type of a lattice also is possible. This also will be a hexagonal lattice. There are various types of stacking sequences which are possible. Okay. This I will just show you, just a minute. Okay. Now, before that, so far we have considered, okay, how to construct the lattices and some basis of filling up interstitial and that is tetrahedral or octahedral voids. Okay, we can construct different types of lattices. Okay, whether it could be an ionic type of a compound, okay, or it could be a alloys or intermetallic alloys, okay, or it could be covalent type of bundle. Okay. Most of the metals, if you look at it in the periodic table, most of them form either FCC, BCC or HCP. Very few go into tetragonal structure. The simple cubic structure, only one element goes. Which one? Polonium. That is the only element which takes a simple cubic. That is the rarest one as far as the elements are concerned. Okay. There are the like magnesium here, this is the hexagonal structure. This is the symbol which we use it. If you look at the book, H is hexagonal, P is primitive, okay. 2 is 2 atoms per unit cell, so it is a hexagonal close packed lattice. Okay. Similarly, this is called as a double hexagonal lattice, which is that ABAC, ABAC, ABAC type of a stacking sequence, because we know that when we take a 2-dimensional hexagonal lattice, okay, in that lattice, like this hexagonal lattice, okay, these are all the positions in which another hexagonal lattice could be kept, or these are all the other positions which the hexagonal lattice could be kept on top of it, correct. These are the only 2 positions which are possible. Okay. If we keep this A position and the next layer in this position hexagonal lattice, next layer on top of A, if we continue, it turns out to be a HCP lattice. Okay. Instead, if A, B is kept here, A on top, then the next layer turns out to be a C layer, okay. Then the next layer is again an A layer. If that sequence, this is called as a, in this many of the lanthanides, okay, they go into that particular type of a structure. Here you see this. This is the unit cell, okay. This is a hexagonal lattice. The other part of it, only the atoms which are there within the unit cell is being shown. These are all the positions which they occupy. Then this is again a position. This one, if you see it, if in this prism type of a structure, an atom was there here, next it comes on the other one, correct? These are all the 3 positions. Essentially, this position, if you rotate it by 60 degree, then we will be getting the other position. That is every alternate position in an HCP lattice where the B position is there, every next position you just rotate it by 60 degree and place it, because that position is also from symmetry consideration equally possible. Okay. There are many crystal structures which form, like I think Ni3Ti goes into this particular type of a structure. Okay, you can verify that. Okay. Then this is another type of structures, yttrium, gadolinium. These transformations occur under pressure. Okay. Pressure induced transformation, many crystal structures can occur. Here what is the stacking sequence? AB, AB, CB, okay, AB, AB, CB, C, then AC, AC, A, and then this will repeat itself. There are many combinations of this type of sequences, that is, we have ABC as a sequence is there, correct? If we take ABC, ABC in this particular form, it will turn out to be a cubic structure, right? if we take the combination as A, it is hexagonal. Okay. If we take it AB, it's HCP. We can have this sort of a sequence which is possible. But if you look at all other sequences, nowhere you find that ABC will come. If anywhere an ABC comes, means that it is an FCC type of a structure. In this structure also, if you see it, it is AB, CB, I think CB, A. This is the sort of a structure. No, C, yeah, CB, A, like this structure comes. Okay. CB, ACA, ACA. This is also a combination of these three, but nowhere the sequence ABC comes, correct? Is there any ABC is there? No, AB, yes, ABC is there, yeah, here it is there, correct. This particular one will be like a fault. This is essentially, if you introduce fault in a particular layer, okay, you can have this sort of structures. Okay. But if you look at the unit cell, this is still a hexagonal one. Okay. The symmetry which it exhibits is only the hexagonal symmetry. Okay. Then there are various structures which we have considered. This is just giving a periodic table, okay, where one can, what are the types of crystal structures which it can hold, either HCP, okay, double hexagonal, that manganese type, BCC, FCC. These are all the structures to which most of the elements in the periodic table fall into. Majority go into FCC, BCC or HCP structures. Okay. Okay, what I will do it is I will stop it here. Okay.